Okay, welcome back to Real Analysis. We are going to wrap up our work in Chapter 7 on the derivative, looking at the section 7.9, which is something called the Darboux property of the derivative. There are other topics about the derivative in Chapter 7, but we're going to omit them from this first semester course in analysis. Maybe we can take up some of them in the second semester. In particular, if you want to read about them, some familiar calculus things called L'Hopital's rule, Taylor polynomials, convexity, concavity, I think applications of the second derivative of a function are among some topics in chapter 7 that we're not going to include in our course here. Okay, so what are we going to do in this video lecture? We're going to talk about something called the Darboux property of the derivative. And just to kind of motivate the whole conversation, I just want to remind you that we have seen by example the fact that the derivative of a differentiable function need not be a continuous function, right? So we know that differentiable functions are continuous, but we've seen examples where the derivative of a differentiable function failed to be continuous. Okay, so it's somewhat of a remarkable fact, given that it need not be continuous, that the derivative of a differentiable function does have the intermediate value property. Right? The intermediate value property is a property enjoyed by continuous functions, but what we're going to show here is that it's enjoyed actually by a larger class of functions. It's enjoyed by derivatives, functions that are derivatives of things. And the derivative of a function need not be continuous. Okay, so let's just get going here. I'm going to state and prove a lemma. There's two parts to it. I'm going to give the first part, the proof of it, leave the second part to you, just changing. You don't need any big new ideas, just sort of changing the relevant details. But what are the highlights? So it's about a function defined on an interval. So I is an interval, f is defined on it, c is some point in I, and I'm assuming that the function is differentiable at that point. Okay, so I don't need to assume the function is differentiable on the entire interval, but rather just at the point c. Good. So if the value of that derivative is positive, if f prime of c is positive, then there's some delta, some positive number delta, so that f of x will be strictly bigger than f of c, not in the entire delta neighborhood of c, but rather its right half. Okay, so if I pick x's that are within delta from c, but bigger than it. So I can just sort of draw a little picture here to help you visualize that if it's not already done. So I'm normally, when I think about a delta neighborhood, I think about c, take away delta, and c plus delta, but I'm just saying take those elements in the interval, so I'm intersecting it with I, that are just in the kind of right half, quote unquote, of the delta neighborhood of c. So if the derivative is positive at c, there's a delta so that f of x is bigger than f of c for every x in that kind of right-sided neighborhood of c. Okay, and I'm going to say this out loud. In particular, that means that f of c cannot be a maximum for our function on this set I, because there are points for which the output is bigger. Okay, f of c is not a maximum. What's the other part of the lemma? The other part of the lemma says, well, if f prime of c is less than 0, okay, then again, there's some delta where, once again, f of x exceeds f of c for all x in the left-hand side of the delta neighborhood. Okay, so the left-hand side of the delta neighborhood intersect I are the points over there. And again, c cannot be a maximum. That's the point of this, that there's some delta neighborhood around c, that there are points smaller than or equal to c in that neighborhood whose outputs are bigger. Okay, so if the derivative is positive at c, there's this neighborhood that f of c cannot be a maximum. If the derivative is negative at c, f of c cannot be a maximum. Okay, so it's how to prove this. I'm just going to prove part 1. So let's take the notation from the theorem and suppose, say, for example, that f prime of c is positive. Well, that means that this limit exists and is greater than 0, right? The f prime of c is by definition the limit of that difference quotient. So if that limit is positive, well, that means there's some delta neighborhood, two-sided, there's some delta neighborhood of c for which if you take x in the domain of f in that neighborhood, the outputs of that difference quotient have to be positive. right? I'm using the epsilon delta definition of limit there, and the epsilon, if you like, could be half of f prime of c. Okay, so if you stay within delta of c, then your output has to be within half of, say, f prime of c. So that in particular, it would have to be positive. Cool. Okay, so that's just an old limit law. And now just by some algebra, if I look at f of x minus f of c, well, it's certainly equal to that difference quotient times x minus c. And here's where the one-sided neighborhood comes in. If I pick x in that delta neighborhood, but I pick it bigger than c, okay? So if that interval notation isn't working for you, I'm just saying that I've got a number x that's bigger than c. And then it's also in my domain, so I can plug it into the function. So if x is bigger than c, then x minus c is positive. So when I look at these two quantities up here, x minus c is positive. We just said if you're in that delta neighborhood, the difference quotient is positive. Well, the product of two positive numbers is positive. Okay, but if f of x is bigger than f of c, or sorry, if f of x minus f of c is positive, then f of x is bigger than f of c. Good. All right, so I'm going to leave it to you to modify that proof in the case that f prime of c is less than 0. You can take a look at the case where f prime of c is less than 0, and then you're going to be saying something about the left-hand side of that delta neighborhood. Okay, so that ends the proof of the lemma. I'm going to use both parts of it. Here is the main theorem of the section of the lecture, Theorem 731 in our book, and our book doesn't give it this name, but a lot of people call this Darboux's theorem, so I'm going to call it that too. And I could have stated it more briefly. Darboux's theorem says if you take a differentiable function, its derivative has the intermediate value property. Okay, so f prime has the IVP is the sort of executive summary of this. But if we kind of walk through the highlights, again, I'll take a function on an interval. Okay, I'm going to suppose it's differentiable on that interval. So I is some interval. I've got a function defined on it. It's got a derivative at every point in that interval. So then if you take 2 points in that interval, say a is less than b, and we suppose that the derivatives there, we're supposing they exist, say they're not equal. If you take a number k that's between them, so k is a number between f prime of a and f prime of b, then there's some number between a and b that f prime will hit the value k. All right, so that just is a sort of expanded version of saying that f prime has to have the intermediate value property. Okay, so I'm going to just kind of prove one case. I'm going to prove the case where f prime of a is less than f prime of b. In the hypothesis of the theorem, I'm just saying they're not equal. But this case is actually quite general. If f prime of a is bigger than f prime of b, just replace everywhere I work with f with minus f, which is also differentiable, and then that's how you get the other case. So we're not really losing any generality. Okay, so I'm going to pick a k between f prime of a and f prime of b, and in particular, I'm making this assumption about k. It's bigger than f prime of a, but less than f prime of b. Okay, so then I'm going to define a function on the interval from a to b, which is a subset of I. Yeah, I'm going to define a function on the interval from a to b, g, by saying that g of x is k. What's k? K is that number between my two derivative values, k times x minus f of x. And I do that for every x in the interval from a to b. Okay, so what kind of properties does g have? Well, it's a polynomial minus f. F is differentiable, so g is differentiable. G is differentiable on the interval from a to b by differentiation properties, Theorem 7.7. All right. If it's differentiable, it's continuous. So g is a continuous function on this closed interval. Well, the extreme value theorem, breaking out a lot of machinery here, says a continuous function attains a maximum on that interval. Yeah, every continuous function on a closed interval attains its maximum and its minimum, but here I'm focusing on the maximum. Okay, but if I look at the value of g prime at a, just differentiate this, stop the video for a second, compute g prime, it's k minus f prime. So if you plug in a, you get k minus f prime of a. Well, k minus f prime of a is a positive number, right? So applying our lemma to the function g, the maximum of g cannot occur at a, right? The lemma says because g prime of a is positive, there's some delta neighborhood that points to the right of A in it in this interval would have a bigger output than at G of A. So G of A is not the maximum value. The maximum value of G does not occur at A. That's by the lemma applied to the function G. All right, but you can also compute G prime of B. G prime of B is K minus F prime of B. Well, that's going to be negative. K minus F prime of B is negative. So the second part of the lemma, the part that I left to prove to you, says that the maximum of G doesn't occur at B either. There's a delta neighborhood around B, points to the left of B in it have bigger outputs than G of B. That's what the second part of the lemma says, okay? But I know G has some maximum on the interval from A to B, so it must be obtained at some point that's interior. So this maximum, I'm calling the input C. G of C is an absolute maximum, and what I was fussing about is that C is interior. Why do I want to fuss about that? Well, because Theorem 7.18 said that if you take a point that's interior to a closed interval, take a differentiable function, at the maximum, the derivative has to be 0. So G prime has to be 0 at this point C. But again, G prime is just K minus F prime. So if G prime is 0, well, that means that K minus F prime is 0. That means that F prime of C is equal to K. So there you go. K was any value between F prime of A and F prime of B. And we've shown that there's some input that F prime hits it. So F prime has to have the intermediate value property, even though it need not be continuous. Cool. So I'm going to end with just a remark that, Darboux's theorem kind of rephrased. It gives us some insight into what kind of discontinuities a derivative can have. So we've seen an example that x squared times the sine of 1 over x, where its derivative wasn't continuous. And in fact, its derivative wasn't continuous at 0 because it was sort of oscillating infinitely fast near 0. But it still had the intermediate value property. So one way to think about what Darboux theorem is saying is that the derivative of a function, if it's discontinuous, it's not because it has jump discontinuities. Jump discontinuities, I haven't really formally defined that, but you know the term from calculus. Jump discontinuities would occur in a function that doesn't have the intermediate value property. So Darboux's theorem says that derivatives couldn't have those. They also couldn't have a removable discontinuity. A removable discontinuity is something that kind of looks like, well, the function's value isn't the right thing. But again, that wouldn't have the intermediate value property. So Darboux says that that can't happen. So that kind of oscillating near the point is the kind of discontinuity a derivative can have. All right, just to illustrate that in kind of one concrete example, if I took a function, say g, defined on the interval from -1 to 1, like this. So to the left of 0, g is -1. To the right of 0, g is 1. And at 0, it's 0. So if I sort of sketched a quick rough sketch of the graph of this function g, what does it look like? It looks like it has the value -1. Up until 0, it's 0, it's 0, and then it has the value 1. Okay, so there's a graph of y equals g of x. And that graph certainly shows that the function g does not have the IVP. Right, for example, if I took, say, the output value 1/2. 1/2 is between g of 1 and g of -1, but there is no x value, no c value between -1 and 1 that hits 1/2. So I can say that that function g cannot be the derivative of any function, right? And it's not just because like I can't think of a function for which that's the derivative. G cannot be the derivative of any differentiable function on -1 to 1, because if it were a derivative, it would have to have the IVP. That's what the Darboux theorem says. Okay, we're going to end it there. Thanks for listening.